This is Lab 5, Faraday's Law for Physics 2212. The purpose of this experiment is to build a computational model of a bar magnet falling through a conducting tube to visualize the effects of Faraday's law. There are three main concepts that are going to be used throughout this lab. The first one being Faraday's law itself, which relates the rate of change of flux through a loop to the magnitude of EMF. PHYS law will calculate the magnetic field as produced by a current, and Newton's second law, which will be used to calculate the net force on the magnet and update the velocity and position as the magnet falls. So in this experiment, we took a regular roll of aluminum foil and a bar magnet and recorded the amount of time it took for the bar magnet to fall through the tube. After 5 trials, the average amount of time that took was 1.17 seconds. The initial conditions used in this lab were the length of the tube being 0.304 meters, width of the foil being 0.000508 meters, and the inner radius being 0.0127 meters. The magnet's mass was 0.025 kilograms, and the magnitude of dipole moment was 4.15. This is a derivation from the magnitude of the dipole moment seen in Lab 3, as that one was calculated to be 10.35, but that did not fit in with this experiment, and in order to simulate the conditions seen in the physical experiment, we had to adjust the dipole moment to be 4.15. This experiment also starts with an initial velocity of 0 and at time t equals 0. So there are a few main pieces here that create our computational model. First one being the calculation of the magnetic field of the bar magnet. This was pulled from Lab 3. The next step is to calculate the magnetic flux and the change in flux over change in time. This is a derivation of Faraday's law. And the result of this step we are able to then use to calculate the current in the ring or the aluminum tube, and this is because of Ohm's law, which relates the current to being voltage divided by resistance. We are then going to use a derivation of the Biot-Savart law in order to calculate the magnetic field at each ring. And then using Newton's second law, we're able to update the magnet's velocity and position and overall see the net force on in this system. So this is our model here. We have the magnet falling through the tube with the south end being the blue side and the north end being the red side. And it's seen that the velocity is changing up until about 0.159 seconds, and at this point it reaches a constant velocity of negative 0.257 meters per second. The time the magnet spent in the tube overall was about 1.161 seconds, and this is about the same time that it was dropping through the aluminum tube in the experimental model. So what if the resistivity of the conductor was reduced as close as possible to 0? This would cause a induced current to be very large, and thus the magnet would fall a lot slower. It would take longer for it to fall through the tube. What if holes or slots were cut into the tube? This would reduce the number of rings in the tube, and this would cause a reduced current and reduced magnetic field, and thus the magnet would drop through the tube faster.